Cylindrical capacitor consists of two conducting cylindrical shells. Inner shell has a radius R1 and outer shell has a radius R2. Then let's find the capacitance of this cylindrical capacitor. C capacitance is given by the general formula, which is Q divided by U. But as we said, that the capacitance depends only to the size and the shape of a capacitor, and it doesn't depend to the voltage applied across its plates or the charge on it. So that's why we need to derive the expression which also includes R1 and R2, the inner and outer radii of these cylinders. To do so, we need to find the relation between U, the voltage, and the charge Q. U is given by the following formula: E dr, where E is the electric field strength inside a capacitor between these cylinders, okay, between these shells. Consider that the inner shell is positively charged and the outer shell is negatively charged. Then electric field lines goes from positive shell to the negative one, right? Then how do we determine electric field strength inside a capacitor? For example, at this point. To find electric field strength, we can use Gauss' law. We can only use Gauss' law if there is some symmetry. If there is no any symmetry, then Gauss' law is useless, right? Because there are some integration, and if electric field, if you can find some surface such that electric field strength is constant on that surface, then definitely this law gives you a chance to find electric field strength in a very easy way. Since this this capacitor has cylindrical symmetry, we can choose our Gaussian surface in the shape of cylinder, okay, in this form. So on the curved surface, electric field strength has the same magnitude at any point on the surface. Okay, so if we use Gauss' law, then the flux over a closed surface, E ds, equals 4 pi k Q enclosed, so the charge inside the Gaussian surface. So since only the inner shell is inside this surface, the enclosed charge is just Q. Now this is the flux. Okay, so on the left hand side you can see the flux over a closed surface. We can divide it into three parts. Okay, so the flux through the flat ends, and also the flux through a curved surface. At the flat ends, ds vector is parallel to the axis, right? And electric field strength goes radially away from the x. So what does it mean? So at the flat ends, E and ds, they are perpendicular to each other, and the scalar product, which contains cosine alpha, gives you 0. The only non-zero contribution comes from the curved surface, right? On the curved surface, for example, take any point. For example, this one. Direction of E goes up. So this is E, electric field strength. And direction of ds vector, it also goes up. The same direction as E. Because ds vector is always perpendicular to the surface and it always goes outward. That's why the angle between them is just 0. So this scalar product could be written as E multiplied ds multiplied cosine 0. 0 is the angle between E and ds vectors, equals 4 pi kq, or just q over epsilon 0, and epsilon 0 is the permittivity of the free space. And from this equation you can find electric field strength, right? First of all, since E is constant on the curved space, you can take it outside from the integral notation, and integration of ds gives you just s. So the curved area is just 2 pi r. Okay, it's just 2e multiplied 2 pi r equals q over epsilon 0. Now from this equation, if you find electric field strength, the magnitude of the field equals just okay, there is also L, right? So 2 pi r multiplied L. So it is 2 pi r multiplied L equals q over epsilon 0. Then electric field strength E is just q divided by 2 pi epsilon 0 L multiplied R. Since we have already determined the electric field between the cylinders, now we can find the voltage U. U is given by E dr. There's also integral. Now E and dr, they have the same direction because E also goes radially, and integration also goes from R1 to R2, right? So that's why the angle between them is just 0. So we get E dr cosine 0, which is just 1. And integration goes from R1 to R2. Now, electric field strength, which we have found, is 2 pi epsilon 0. And here we also have Q divided by RL, or we can also write just L, and multiplied dr over R, and integration goes from R1 to R2. If we integrate 1 over R, we get just ln R. Okay, so it is Q divided by 2 pi epsilon 0 L ln R, and integration goes from R1 to R2. Then if you put this R1 and R2, you will get ln R2 minus ln R1, which is just ln R2 divided by R1. Then capacitance C equals Q divided by U, which is just Q divided by, so okay, here we have Q multiplied 2 pi epsilon 0 L, and also ln R2 divided by R1. Now canceling this Q, we get two pi epsilon 0 L ln R2 divided by R1.